Kia ora and welcome to the last question in the 2023 Skull Calc exam. This question is all integration. First one, we've got an area between two curves, which is pretty straightforward. The second one, we've got an integral that's actually easy to find, but they throw in some limits to confuse. The third part, the asteroid from the 2022 exam returns. This time we're finding its perimeter. I think in the year before we were finding area. The area integral was a mess. This one actually falls out really nicely. And then the fourth is a function that is defined as the square root of an integral. And so to solve this problem, we actually need to use the fundamental theorem of calculus, which is the thing given in the hint. Okay, so the first question here is a really nice start. When you find the area between two curves, you just need to integrate the difference between the curves. The top function is 6x minus x squared. The bottom function is x squared minus 2x, and it's always the bottom function. And we integrate that with respect to x between 0 and 4, because they're the bounds of the region. The function 6x minus x squared is equal to the other function x squared minus 2x when 2x squared is equal to 8x, or when x squared is equal to 4x, that's x equals 0 or 4. Now you don't have to worry about the fact that this region goes below the axis. Okay, it's a common misconception that students might have. Like when we take the top function and the bottom function and we find the difference between them, if the bottom function's negative, which it is in this case for at least a little part of it, then when we say this value here might be y1 and this value y2, if the y2 is negative, when we subtract it, when we go y1 minus y2, we're actually adding. And so we get the whole length. We don't need to worry about the axes. So this is y1 and this is y2. We just integrate the difference. So that can simplify. 6x minus 2x is 8x. Negative x squared minus another x squared, and we're integrating that between 0 and 4. 8x antidiffs to 4x squared, minus 2x squared antidiffs to minus 2x cubed over 3. And if we sub in the 4, subbing in 0 obviously cancels, we get an answer of 64 thirds. Okay, part B, evaluate the definite integral here. Now this is kind of weird, because in the region from 1 to 4, this expression is actually not defined. There's a discontinuity at x equals 2. If you graph the curve, so have a look at what y equals 1 over x minus 2 to the 2/3 looks like. It has an asymptote at x equals 2. Which you might think, oh, because it's undefined, we can't find this integral. But it's not a whole region where it's undefined, it's just a particular point. And so actually this integral can be found. It's called an improper integral. And that's what the limits are suggesting. If you completely ignore the limits, you actually get the right answer, which is really interesting. But let's integrate this. Integrating between 1 and 4. Oopsies. 1 and 4. 1 over x minus 2 to the 2/3. We break it up to 1 to a little bit less than 2. So I'm going to put a k there, just like the hint kind of suggested. And I'm going to write limit as k goes to 2 from the left, which is the negative side. So we're talking about something like 1.99999. And like I was saying, it turns out we don't need this because the answer comes out the same if we didn't do this step. But this is proper mathematical notation. And we also want the limit as x approaches 2 from the right-hand side, the positive side of this dude, between k and, why am I saying x approaching 2 plus? I mean k approaching 2 plus k to 4. Okay, now both of them obviously are the same function, so they've got the same antiderivative. It's a power of negative 2/3. When we increase that by 1, we get 1/3. We divide by 1/3, it's the same as timesing by 3. So we end up with 3 times x minus 2 to the 1/3 between, this is really dodgy, but I'm just going to write 1.999, etc. plus, because I guess at NCA level 3, your understanding of limits can be informal. It's not till university maths where you actually have to be a lot more well-defined of what you mean by limits. And then this one's going to be 2.00001 and 4. So if we substitute in the top limit 1.999, etc., then the thing in the brackets is going to be pretty much 0, slightly negative, but 0. 0 to the power of 1/3 is 0, so that limit does exist at 0. And then we've got 3 lots of 0 minus, this is where be careful. If we sub in the bottom limit of 1, the bracket becomes negative 1, and we're taking the cube root of negative 1. The cube root of negative 1, there are 3 answers to that, but we want the real solution. So if you go on the calculator, the cube root of negative 1, if your calculator's set up to real mode, it will just say -1, like it probably did since you were year 9. But if you've got it set on complex mode, then it's going to give you an imaginary number. You don't want that one. You want the real solution. So the cube root of negative 1 is negative 1. Okay, do the same thing for the other one. If we subbed in the top limit first, 4 minus 2 is 2, the cube root of 2. 3 times the cube root of 2, which is a irrational number, so we'll just leave it like that. And then if we sub in the bottom limit, which is a number just a little bit bigger than 2, that makes the bracket go to a number just a little bit bigger than 0. The cube root of that is 0, and we get 3 multiplied by 1 plus the cube root of 2. And that's the answer you would get if you had completely ignored the limiting bits, because both of the limiting bits were 0, so they had no effect on the final answer if you just integrated from 1 to 4. Okay, home stretch, part C. We've got an asteroid that we want to find its length using this formula. You need to be careful of your limits for this, and I'm going to explain, but if you were to go 0 to 2 pi, you actually get a pretty strange answer. You get the answer of 0, which obviously that perimeter is not 0. A really good thing to do when you've given a picture like this is to approximate. So if I was to draw a straight line from the x to the y-intercept, that's going to have a length of square root 2 by Pythagoras. And there's 4 of them, so if I go 4 times root 2, I get an answer of 5.6. So the perimeter is going to be a little bit longer because it's a curve and not a straight line. An answer in the ballpark of 6. It turns out the answer is actually 6. At least you know kind of what you're aiming for. Okay, so we need to take this integral and substitute derivatives into it. We'll talk about the limits in a sec. So L equals the integral from t1 to t2, square root dx dt all squared plus dy dt all squared dt. Now x was equal to the cosine of t all cubed. It was written as cosine cubed t, but that's what that means. The y value was sine of t all cubed. Differentiating these using chain rule, 3 cos squared times the inner function differentiated, which is minus sine, and dy dt, 3 sine squared t times the inner function differentiated, which is cosine t. The chain rule was so important, it pretty much comes up in every question. Now, it looks like it's going to blow up in our face. We're going to square these and add them. So the length becomes integral t1 to t2. I'm going to still deal with these limits later. The square root of the first thing squared, which is 9 cosine to the 4 sine squared. The minus cancels because we've got minus times minus. And then the second term is 9 sine to the 4. I keep writing the t up in the power. What am I doing? Times cos squared dt. Now, when you look at this, you go, how the heck am I going to integrate this? Well, trig identities are helpful. So is some algebraic simplification. And the idea is that we've got a common factor underneath the square root. So we should use that. The common factor is 9 cosine squared for each of the terms and sine squared for each of the terms. And then the brackets, well, the first term has another cosine squared, and the second term has another sine squared. And that, my friends, is equal to 1. And then we can square root the stuff in the front because it's now a product. Originally we had a sum of two things. We've turned it into a product, so we can square root that. Now this is where you've got to be very careful, because the square root of something squared is technically the absolute value the square root of x squared is actually the absolute value of x. Okay, it's not just equal to x, because if x is negative, like what is the square root of minus 5 to the power of 2? Minus 5 squared is 25. Root 25 is 5. Okay, it's the absolute value of the thing we started with. So we've got to keep that in mind. And technically I should put the absolute value of 3. Well, we can pull the 3 out. The square root of 9 is 3. We can pull the 3 out in front of the integral. Let's do that. But it's the absolute value of sine times cosine. And we can only lose the absolute value symbols if those two things multiply to a positive number. So that's where we need to consider our quadrants. If we go up into the first quadrant here, both cosine and sine are positive. So when we multiply them together, we get a positive number. And what you need to realize is that this is t is equal to, what is it equal to? T is equal to 0. And this dude here is t is equal to pi over 2. If you weren't sure about that, we look at our x expression. When we make t is equal to 0, we get x is equal to cosine of 0 all cubed, which is 1. And when we make t is equal to pi over 2, we either get x equals 0 in the first one, or we get y is equal to 1 in the second equation. Okay, so in that quadrant, both cosine and sine are positive, which means they multiply together to give a positive, and therefore we can just drop the absolute value symbols. Okay, but that means what we want to do is write 12 lots of the integral between 0 and pi over 2 of cosine t sine t. 12 because I'm finding one quadrant and then I'm timesing the perimeter by 4. Cos t sine t, why have I done that? Why has the simplification helped? We've got a double angle formula on the formula sheet, which is this one. We can exploit this by putting a 2 there, changing this to a 6. So we're integrating 6 multiplied by this integral here, which is actually just going to be sine 2t, because I can anti-diff that without using integration by parts, minus cosine 2t all divided by 2 between pi over 2 and 0. And then subbing in pi over 2 into that first cosine of pi, which is negative 1, we've got a minus half factor, so it equals positive 1/2, minus, subbing in 0, we get cosine of 0 is 1, so it's minus 1/2. You've got to be real careful with integers and double integral, definite integrals. 6 times 1 equals 6. Now, just to go back to that limits, if you had 0 to 2 pi as your limits for here and here, you would have got an answer of 0 because your integral expression is periodic and it repeats every 2 pi. So you would have got 0. We split it into 4 and that's how we work it out. Okay, last question. Very strange problem. Never seen one like this in scholarship before. We've got some function that's written in terms of itself. Because on the right-hand side, we've got the integral of f of t squared and f dash of t all squared. Strange little bit of notation, the squared really should be on the inside there, but it's not a big deal. But how are we supposed to find that integral if we don't know what the function is to begin with? It's a bit of a weird problem. Turns out though, if you square both sides of this and then differentiate, you solve that problem. So, part D, f of x is equal to the square root of the integral between 0 and x of f of t all squared plus f dash t all squared plus 2023. Gotta love it when the year comes up in the skull problem. Now, squaring both sides first. So we've got f of x all squared. We lose the square root on the right hand side. And technically we are, oopsies, we're integrating with respect to x. We're integrating the whole thing here. Okay, now how do we differentiate this? Well, differentiating the left-hand side, it's something squared. So that differentiates to 2 lots of something times the something differentiated. That's chain rule. It's also implicit differentiation. Sometimes you would have seen it as maybe y squared differentiates to 2y times dy dx. It's the same idea there. There's the y and there's the dy dx. Now the right-hand side, this is the really sneaky part. If we differentiate this with respect to x, actually we lose the integral symbol because the bottom limit is a constant and the upper limit is x. We end up just with f of x squared. Actually, hold up, where is that 2023? I think I've stuffed this up. The 2023 is not being integrated. It's underneath the square root, but it's not in the integral. That's important. Okay, let's get rid of it there. Otherwise things wouldn't have simplified nicely. And let's get rid of it in that bracket too. Oopsies, put my dx in there as well. Okay, so yeah, when we differentiate the right hand side, we actually just get f of x all squared plus f dash of x all squared, and the 2023 cancels. Now this is really sneaky of them, but this is a perfect square expression. If you rearrange this, I'm just going to write f squared because I'm being a bit lazy at this point. F dash squared, and then we're minus 2f f dash. That is the same as f minus f dash all squared. And that, of course, only equals 0 if f is equal to f dash. Therefore, dy dx is equal to y. Separating the variables of this, or just recognizing what the solution is to it. Log of y is equal to x plus c. Y is equal to... y has to be positive, by the way, in this question, because we've got a positive square root function. So f of x is a positive expression. We can drop the absolute value symbols there. We get e to the x plus c, which is the same as a e to the x. And you might think you're done there because, like, they didn't give us any information other than this integral. Like in the problem, normally when you have to find a constant, they actually give you a point to substitute in. But they've given us nothing extra, so hey, is that the answer to the problem? Is it just a e to the x? Well, it turns out that we do get a little bit of information from this because we can sub in x equals 0 into it. If we sub in 0, we get f of 0 is equal to the square root, and this is where the fun happens, the integral between 0 and 0 of something plus 2023. Now, an integral between 0 and itself is equal to nothing, so we end up getting root 2023. And f of 0, when we've got a function that's y equals a e to the x, f of 0 is the a value. That means that a is square root 2023. So we can work it out, and our final function using f of 0 is equal to the square root of 2023 implies that y is equal to root 2023 e to the x. And that's the SCOL exam for 2023. I hope you found these videos useful, and all the best as you use them for 2024. If you're watching them before the summer, have a great summer. You've deserved it.